Hi, everybody. Can everybody hear me?
Yeah.
Okay, wonderful. I hope you had a good weekend. Are there any questions from the homework you did over the weekend? Concept questions or whatever before I continue? Okay, well, let's get going then. Get this done. Now, some announcements first. Basically, what's happening is the lab this week, Dr. Gerhardt is working up something. He will do a virtual lab for half of the lab you're going to do next week, the non-metal reactions of non-metals, and as well as a pre-lab. And so he wants you to do, and I do too, to do both of those things. Watch the pre-lab and the video lab for the non-metals portion of the metals non-metals reaction laboratory. And basically, you'll just start filling in the paperwork, and then you're done. Next week, we'll come back and we'll finish off the metals part and work on another lab in person. So basically, those are relatively short, but they're good labs anyway. So that should help explain it. Now, the quiz I had planned for today, I decided to wait on it because there's some stuff at the beginning of the next chapter that's very useful for the quiz. So, and kind of connects with what we're doing already. And so basically it's just a bookkeeping thing, but there's a possibility if I do well today and on Wednesday, we might have the quiz on Thursday, but I'm just delaying it just to give you more time and just to get ready for it. The test will be after we have chapter 7. So basically, because chapter 6 and 7 are relatively short, the test will probably be in 2 weeks when you're back, and then the first week of November. Are there any questions about the upcoming schedule?
So our test 3 will be the first week in November. Is that our last unit test before our final, or do we have a test 4?
No, the last week of the exam. The last week of classes before the final. That Thursday will be your last exam. So there'll be 4 exams.
Okay, and the final exam is cumulative?
Yes, it's a whole semester, correct. And it'll be one that the department comes up with as a way to test everybody with the same criteria.
Okay.
Okay, any other questions? So we'll have a quiz on chapter 6 that we just finished, as well as one on 7, just to finish it up. And the quiz is, again, a reminder just for practice and such like that. But I may have a take-home worksheet on it too. I haven't decided yet how it goes. But our first in-person lecture will either be next Monday or next Wednesday for the lecture part. I haven't decided yet. We'll see how it goes regarding it, because if it's just, it may be easier just to do a Zoom meeting on Monday, just if I have some just general stuff to work and we really don't need to do it in person. But we'll see how those things go. Any other questions regarding that? Okay, let's get going with the PowerPoint now. Basically, what I'm going to do is continue with the chapter, but you'll find that it is very helpful, and that it will be very, very compatible with what we've done already. And so basically, we'll just continue where we left off on last time. So let me pull it up here. And you'll see this is just general information regarding it. I'm going to share the screen with you now. Hold on a minute. Let me go back to the thing again. I've got the PowerPoint going. Okay, now we're going to essentially talk about the periodic table and finish up where we left off regarding this. Hold on, I want to do some slight thing to kind of get another relationship here. Okay, I just wanted to check the thing to see how this was going now. So let's get this moving. All right. Okay, I'm going to share the screen now with you. Okay, now what we're going to do is essentially talk about the elements, talk about when the elements were discovered. If you remember when I was talking about the naming, like boron, nitrogen, carbon, etc., there are a whole bunch of discussed that are in ancient times, like carbon, sulfur, iron, copper, silver, and gold. And basically, they were all very important in medieval times, as well as going all the way back to the Bible. And there's a whole bunch of elements mentioned in the Bible, like sulfur, iron, copper, silver, and gold. They're all mentioned in the Bible, and in a way I find it very interesting that there are even some procedures talked about in there, like, for example, the destruction of Sodom and Gomorrah, where it talked about things made of salt, pillars made of salt, as well as the sulfur burning and such like that. So it's very obvious that there was a lot of people that were aware of elements earlier. Now, then you get the Middle Ages up to 1700. They got phosphorus, arsenic, antimony, zinc, and platinum. And so basically, tin was also here. That was in ancient times, as well as lead. So and as well as mercury. So all these were important, particularly the combination of tin and copper, which made brass. So basically, brass was quite, bronze. Bronze was quite important in ancient times as well. So I hope that makes sense regarding the nature of the names, because the simple names are taken first, like boron, nitrogen, oxygen, carbon, sulfur, iron came from ferrum, agrum was silver, arum was gold, and so they're all related to the Latin. So basically the ancient Romans and Greeks had their own names, and some went to the English. So it's very interesting how it all worked. Now, let me go. The ground state electron, this is the electron configuration, the elements. Now, there's some things that you need to realize. Some chemistry teachers would give you this table and say, memorize it. But say, for example, with what you were doing over the weekend, if you wanted the thing for magnesium, you could do your finger on it, 1s2, and then 2s2, 2p, count 1, 2, 3, 4, 5, 6, 2p6, and then 3s2. And then you could kind of break that off and make that neon in there for the abbreviated form. And on our quiz, remind you that I would like you to know the full one. But if you look at this periodic table, it has the ground state electron configuration of the elements. So basically what are here, these values here, these are called the valence electrons. And they're the ones in the outer shells, and they're the ones involved in bonding. So it's very, very important, these outer shell electrons, because essentially what we learned is that what all the elements want to pretend to be is the thing that have 8 in their outer shells, except for helium, which has 2, but all of these have full shells associated with them. So they're like a billiard ball and essentially a nice tight thing with everything, all the electrons evenly spaced through the whole system. Does that kind of make sense? That if you got the center here, the nucleus that's positive course, and then all these electrons going around it in all the right forms and everything. So when it's full, it's essentially a solid thing and no reaction when it's full. And again, pardon my art, but the point is, when it's full, it doesn't want to give up electrons or share them. So basically, these elements on the right don't react with anything. Now, again, yes.
Dr. Douglas, I'm sorry to interrupt. I had a question. So, for example, regarding krypton, on the valence on this chart, it says 4s2, 4p6.
Right, that's the outer shell, correct.
Yeah, but what about the d values? It only has the s.
Well, because as I was saying before, the d values essentially, when it is tight, the d ones are outside the valence electrons, and unfortunately, this periodic table is a bit misleading because 3d10 is in here also. So basically, they're just doing the outer shell here. So you have 3d10 in here too.
Okay, so but on the quiz that we have on Wednesday, you'll want us to include the d values as well.
Yes, correct. So basically, you just go over it like this would be 4s2, and then this is 3d1, and then this is 3d10, etc., and then over to 4p6. So basically, it's just a matter of following what I suggested. But as I was saying, with the periodic table I gave out to you, the 1A, 2A, and everything, when we had 1 plus 1 plus 2, and then plus 3 over here, those are all related to the NS2 here, NP up to 6, 1 to 6 here, and then this is N minus 1 D, and then this value is N minus 2 F. And if you look at this chart, see how it goes 6s2, 5d1, and then it goes down to 6s2, 4f, 5d1, 6s2, 4f, 1, 5d1. So essentially it fills up the F shell going all the way over to 14, and then it goes back up to the D, and you have 4f14 in there as well. They're just trying to save space when they fill that in there, okay?
I'm sorry, Dr. Douglas, I have another question. So say, you're doing one of the D values like OS, I don't remember what it's called. You would do, the 6s2, 5d1, and then f12, and then do the other D values after that?
Well, no, you could do 4f12, 5d2. So HF would be here. HF would be the thing. You go to the one below it, that'd be xenon, and then it would be 6s2, 5f14, 4f14, 5d2. Okay.
Okay, but what about the LA value?
Well, LA would be essentially the xenon for LA would essentially be 6s2, 5d1, because the d1 goes in first. But remember, if you remember the shapes, the d1 really doesn't matter. The 5d is just a little less energy associated with it, and it's just one electron, so the orbit really doesn't matter anyway. It'll share the f orbitals anyway, just based on its energy.
Yeah, no, I understand that part. With the OS, it would kind of be like D6, because that would be the 6D value.
OS again, that would be xenon, okay, and then 6s2, 4f14, and then 5d6. Okay.
Oh, okay, gotcha. Okay, I understand.
And some people use that other chart where you go across like this. I don't like it because it's too confusing. I don't recommend that to the students. I just rather have you just go across the periodic table graduate, follow the numbers. And like this is 57, this is 58. So just follow it and be logical about it. That's the value of this periodic table, okay? Now, one of the things that many of you brought up earlier in the semester, and I think people may even complain about it, that I was asking, wait till later chapter. And this has to do with where does the oxidation state come from, folks? Like the oxidation state for magnesium was +2. Where does that come from? What is its electron configuration? Well, if you look at the thing, it'll be neon, okay? And then magnesium is 3s2, right? So if it's +2, what's going to happen to the 3s electrons? They go away. So that is why the magnesium +2 is stable. It's a very happy atom. It is pretending to be neon. It's pretending to be noble. Okay, so let's go to the next slide. And I'm going to erase what's on this slide now. The slide is better, but basically we just go to the next slide here, and then you have the NS2 and P1. They're going across, and these slides are useful also. And then you've got the D1s there, D5, D10, going across, and then 4F down at the bottom, and then 5F. Now, the classifications of elements, the representative elements, those are the ones that are most common. These are the most common ones. And essentially, all of these have similar chemistry. So as you go down the thing, there's similar chemistry associated with them. Okay, so basically lithium will react like sodium, will react like potassium because they're all +1. Beryllium will react like magnesium, calcium, strontium, and barium because they're all +2. Okay? Boron, aluminum, gallium will all be +3. So you have +3 associated with that. Well, here, this is 2s2, 2p1. So essentially that removes those extra electrons to get the +3. Okay? The noble gases are over here. The noble gases then, the transition metals, these are the ones that are down here, and those are essentially considered all these in here, and they are essentially the ones using the d orbitals filling up, okay? And then the lanthanides and actinides, these are the f orbitals. And basically all these elements down here, these are essentially x +2 or 3 usually. But uranium could be UF6 associated with that. So uranium can go all the way up to uranium +6 for an oxidation state. Okay, why would uranium have an oxidation state of +6? Let's have this be a quiz. Why would uranium be +6? I want you to use your finger and count. Why? Brandon, can you tell me why is it +6?
It has 6 extra electrons to give up in order to become a noble gas.
Yes, right. Because radon is the basis. So you got radon here. So it's pretending to be radon. Okay? Because essentially all these electrons have been removed. Essentially, these were electrons removed to get +6. Okay? Does everybody understand that? Okay, let me continue. I'll erase what's on the slide just to clean it up a little. Okay, now electron configurations of cations and anions here. Well, here, this is sodium. Look what happens to the ion. Does everybody see that relationship? What happens to it?
It loses an electron.
Yeah, it becomes neon. It likes to have that, okay? it loses valence electrons. Valence electrons. Okay, those are the ones in the outer shell. Okay, so if we continue with that, calcium looks like that. What charge will that have?
+2.
Very good, wonderful, okay? Go to the next one there, that's +2, it's pretending to be argon. How about aluminum? What's gonna happen with that one?
+3.
Yeah, very good, very good. Okay, and then atoms lose electrons to the cation has a noble gas outer electron configuration, following what's called the octet rule. All atoms like to have 8 electrons in the outer shell. Okay, that is full. They're stable, they're full there. That's called the octet rule, and we'll talk about that a little later, okay? But essentially, all of these, this has 8 electrons, this has 8 electrons in the outer shell, so does that. Okay, because of all of these below, this is 1s2, 2s2, 2p6, right? This is the 8 electrons in the outer shell. This one is 3s2, 3p6. These are the 8 electrons in the outer shell, okay?
Dr. Douglas.
Yeah.
So with the d orbitals, I know it's like n-1. So with aluminum, why wouldn't it be 3s2?
Because there aren't enough electrons to go up to the 3d10. 3d10 is a higher level. It has to fill up the p orbitals first.
I thought it went SDP.
Well, let me go back on the slide. See aluminum here goes 3s1, 3s2, 3p1. These have to fill up first before it'll even get to the D. And if you remember that from the previous chapter where we had the building up principle like this, 1, 2, 3, and then this one for the third, 1, 2, 3, and then the 4, this is 2, this is 1, this is then 4s here, and then 1, 2, 3, 4, 5, this is 3D, and this is 3P. So essentially, these overlap with the 4s, these fill first. If you remember from the previous slide from the previous chapter.
Okay, yeah, I remember. Thank you.
Okay, and that's why I'm including this stuff in the quiz, because it's a nice connection to it, because we're just talking about the electron configurations and then going in that direction. Okay, so basically they're all becoming that, okay? Now let's look at hydrogen. It will gain 1 electron to go to -1. Fluorine, what's going to happen with that? How can it get 8 in the outer shell?
It'll lose an electron?
No.
Or
Count
gain an
them.
electron, sorry.
How does it get 8 in the outer shell? The 2s and 2p. How does it get 8 there? What's it have to do? It doesn't lose an electron. What does it do?
Gains an electron.
Yeah, very good, very good. It gains 1, so now it's neon. That's the electron configuration for neon. So fluoride is very happy, as is, okay? It just happens to have a negative charge associated with it. Oxygen, this is why oxygen is usually -2. How many electrons does it have to get?
2.
2 of them, okay? Now, do all of you get the connection between what I talked about a couple chapters ago and this stuff now? And that's why I said that, be patient. We'll explain that a little later, because many of you were thinking ahead a couple chapters, but there are a lot of students that don't think ahead that far, but you folks are doing it. So I wasn't giving you the brush off when I said we'll discuss it later. But now, doesn't it make more sense though, based on the fact you have the understanding of electron configurations, because essentially what this does is it adds 2 electrons to it. Okay? Does that make sense to everybody? Any questions? Okay, so nitrogen can be -3. Why? It gains 3 electrons and pretends to be neon also, okay? Atoms gain electrons to the anion as a noble gas outer electron configuration. They're all trying to get that. And so it basically wants to have the NS2, NS2, NP6, for a total of 8 electrons in the outer shell, okay? Cation representations of them. Well, this is the outer ones involved in it. So basically, you get these different ones. And again, I don't know the point of adding one more periodic table, but that's what they do. When you have anions and say, oh, okay, that's what you're doing. Okay, so basically they're combining it together, and that's why about a month ago, I asked you on the periodic table to go across the blank one, put +1, +2, +1, 2, or 3, +3, plus or -4 here, and then this would be 0, and that's what I was talking about with that when we did the oxidation states in the earlier chapter. Now, there's some important terms. One of them is called isoelectronic. It has the same number of electrons and it's the same ground state electron configuration. And so basically that's saying that aluminum +3 and sodium +1 both have the same ground state electron configuration. Okay, so they are called isoelectronic. Now, what do you think is a smaller atom? Think logically about it. Sodium ion or aluminum ion? What is a smaller atom? Remember, they've got the same number of electrons going around it on the outside. What's going to be a smaller atom?
Sodium.
Not quite. You might think it would be, but not really. Aluminum will be because there's much more positive in the center and only +3 around it. So there's a +3 charge extra on the center, the nucleus. So basically the aluminum +3 will be a smaller atom. So this is a smaller atom. This is larger than the sodium ion, okay? And that's called ionic radius. And we're going to talk about that on a later slide. But basically, this is where it comes from. Essentially, where is aluminum on the periodic table? What number is it? Look on your periodic table, folks. What number is aluminum?
13.
13. So it has 13 protons, right? What number is sodium?
11.
11. So they're 11 protons, okay? So if they have the same number of electrons around them, so this has 10 electrons around it, and this has also 10 electrons, which is going to be the smaller atom? And just be logical. There's a bigger charge difference between the 13 protons and 10 electrons. So which is going to be the smaller atom? Well, it'll be aluminum. Okay. And then fluorine. Sorry, someone had a question?
I'm sorry, how does that make it smaller if there's more protons, like more, atoms or more protons within the atom? How does that make it bigger?
Because it's a higher positive charge in the center, so whatever electrons are there get dragged to the center better. It's more positive, like it's called a charge difference. There's a bigger charge difference, and those electrons will get tighter in the ball, so to speak. Okay? But when you add electrons, like if let me erase part of this using the eraser here. When you add electrons to this, what's going to happen if you add electrons to this? Like the fluorine -1. This is -1. This adds 1 electron to it. This is the largest. Why? On the periodic table, what is the fluorine? What number is it? How many protons does it have? It has 9 protons, okay? But it has 10 electrons, okay? So what's going to happen to the electrons when there's only 9 protons? Are they going to be farther away or closer? They'll be farther away. So essentially the orbit will be bigger than it was before. This is the first, and then this is F minus, because this extra electron is flying around it. It expands the whole thing. Okay, then if you go to these, adding them to, they're called, all these ones are isoelectronic with neon. What neutral atom is isoelectronic with hydride? Well, if you go 1s2, that's the same electron configuration as helium. When a cation is formed from an atom of a transition metal, the electrons are always moved first from the ns orbital and then from the ds. So if you look at some examples here, like iron, explain what happens to make iron +2. You're going to form iron +2. What's going to happen to make it +2?
Lose the 2 4s electrons because the d are more stable.
Right, very good. And in that case, the whole thing drags down, and so then you've got the argon there. And I'll erase what's on the slide and show you the next thing in their handwriting, in their typing. But basically, it goes to 4s2 that way, and then iron +3. This is because 3d5, which looks like this, 1, 2, 3, 4, 5. There's a rule that basically has to do with half-filled orbitals are more stable. This is 3d5, and so with ferric, this would be 3d5. So that's why there's a +2 and a +3 for iron, because essentially this is more stable than 3d6, which would be this one, okay? This one is more stable, 3d5. So basically you can have 2 irons, ferric and ferrous. This is ferric. This is ferrous. Okay, and that's something that early chemists realized too, that iron could have different colors associated. It could be brown or it could be black. And the different colors and different irons has to do with what kind of, whether it's +2 or +3. So that's some anomalies. Now, manganese here can be +2. Okay, you got +2 for the oxidation state. This is the most stable. Why can manganese be +7, like in potassium permanganate? Why can it be +7? What's going to happen to have it be +7? What's going to have it be so it can be +7? Which electrons does it lose?
It would lose the s and the d electrons and become
Correct, very
argon.
good. And so that's why permanganate is a very common ion. Permanganate ion is a very common ion, very common. and potassium permanganate, very important chemical, okay? But basically, the key thing is they all want to pretend to be argon, or in this case, have the half shell, which is below the s orbital anyway, so it's more stable because it's half filled. This one is half filled there. Now, effective nuclear charge, Z effective is the positive charge felt by electron, okay? So basically that is equal to, there's a shielding constant associated with that. And the effective nuclear charge is a Z minus the core electrons associated with this. So if you look at the different elements here, the core, this is why it's a +1, sodium +1. This is magnesium +2. Aluminum +3, they're all isoelectronic, and then silicon is +4, can be +4 there, okay? The Z effective would be the difference between them, and the radius associated with each of them. Why is the silicon ion the smallest? See, this is the radius in picometers. Why is this one the smallest? Silicon there. Why is that the smallest? Well, because
did you not say something about it having like more electrons? I mean, more protons, something like that.
yeah, more protons. There's 14 protons in the center and 10 thing. Oh, and I'm sorry about that. Let me go back to the periodic table again. Yeah. Okay, so essentially the smallest, as you go across the periodic table, this is the smallest because there are 14 protons and there are 10 electrons. And so the effective nuclear charge is +4. So essentially that makes it very tight. It drags what extra electrons are around it inside it. Okay. Now, as you,
will you go back for 5 seconds?
you had a question about this?
Yes, sir. I'm just what does like the Z stand for and the ZF? Like I'm not really sure where that came from.
Well, it's effective nuclear charge. It's like the difference in charge between the positive center, which is this is the nucleus, right? This is the nucleus here for each of these elements. You got sodium thing, they're all the nucleus. This is the number of protons. Okay?
So Z is equal to the number of protons.
Right, correct. And then the core electrons, these are all 10. These are all isoelectric. Okay, isoelectronic. They all are pretending to be neon. Okay? So the smallest one is going to be here, the silicon, which is +4, because it's lost thing. There's a difference between them is 4, so it's going to be the tightest. And just be logical regarding charges, like in a magnet, you got north attacking south, okay? But if you got a charge difference like +14 and -10, that whole thing will bring in the 10 much closer because it wants those extra electrons to kind of come in closer to essentially make this to kind of neutralize the charge of the center. In other words, the nucleus requires the electrons to be around it, and so it drags the nucleus requires electrons to be around it, so the nucleus essentially drags those electrons that are there closer to it and makes it tight. So the silicon is the smallest radius. Now, as you go down the periodic table, essentially they all have the same trends. So you get increasing Z effective because over here, for the ions, this would be +3, this would be +4, going across +3, +4. Essentially, as you go across, these will get smaller. Okay, but as you go down, because it's going from n equals 1, 2, 3, 4, 5, 6, 7, this outer shell, the s orbital, is getting bigger, so the effective nuclear charge will get larger because you have more protons as you're going down the periodic table, but it goes smaller as you go across. And that's related into what is called atomic radii. So the atomic radii, for example, here with a metallic radius, this is the distance between, say this is a sodium atom, and this is another one. And the electrons are kind of flowing around it. The extra electrons are flowing around it there. So you have +1 there and a -1. So essentially, these all come together. That's called the metallic radius. But this also can explain why they conduct electricity. Because they got all these extra electrons in there. Whereas a covalent radius there, but we haven't talked about bonding yet, the covalent radius is the distance between them when they're sharing electrons. These are sharing electrons between them. So this radius will be different. Now, this is increasing atomic radius, or as I like to do it, it gets smaller as it goes to the right, and then it gets larger as it goes down. Now, if you got my standard periodic table, you can do the same thing. Like just looking at this chart, and if you remember the trend, which is the smallest atom? Lithium, or neon? Which is a smaller atom, lithium or neon?
Neon?
Neon, right, because it has a lot more protons in the center, dragging all the electrons in very efficiently, okay? So essentially, as you go across, the atomic radius gets smaller as you go down, goes to the right, or larger as you go to the left. But I like it smaller as you go to the right. It makes a little bit more sense, and you can kind of picture that in your mind when you're asked which is smaller, phosphorus or sulfur.
So the ideology behind it is the more protons you have, the closer it is to the nucleus, the smaller it'll be. But how does that, then how do you go to the next row and have neon
Because there's an
smaller
extra
than
shell.
sodium?
Because it's a bigger shell. Because going down to the next row, you're going out. This is n. Remember, this is n equals 1, n equals 2, n equals 3. It's like layers of the onion. As you make the onion bigger, what's going to happen? There's going to be more electrons that go around it. Okay, so it's going to be bigger. So it essentially moves back up again. So argon essentially goes from 98 all the way up to 227. Now, what do you think is smaller, argon or potassium +1? Which is going to be a smaller atom?
Potassium +1
Why?
has another proton.
Yeah, one more proton. Very good. Okay. So when you bring in ions in there, they'll be smaller. Okay. And calcium +2 will be even smaller. And they have proved that, which is quite cool. The chemists have proved it over the years. So it's very interesting how these works, and this is how they kind of measure these things. And essentially, they go all the way down lithium, then you get all the way down to fluorine, sodium goes all the way down to chlorine, potassium, then to bromine, etc. And they're all trends associated with that. Now, if you compare them to ionic, here, the radius as you go from lithium which is on, this is n equals 2, right? This would be n equals 2. Why is cesium 2, 3, 4, 5, 6? This is n equals 6. Why is cesium larger? Why is cesium larger? Well, it's on an outer shell. You have n equals 6. It's like, instead of here, the first one, it'll be 1, 2, going out the outer shell here, all the way out to n equals 6. So that's your cesium. That's why it's larger, because you're essentially adding shells to it. Okay, now, if you have the reaction between lithium and fluorine, why does lithium get smaller than fluorine there? Well, it's losing electron. There are essentially more protons in the center, so it drags them all in there. And you add an electron to fluorine, essentially it gets very big. So they shift there. The cation is always smaller than the atom from which it's formed. Now the radons of ions and things too. This is also a thing, this was I addressing before. So basically, these ionic radiuses go over this way as well. And so basically, these essentially follow the same trends. And again, it's as you go across the periodic table, it gets smaller for the same reasons. You have more protons in the center, and then it pulls them all closer together. Now, chemicals in action here, the third liquid element, don't worry about that. The ionization energy, we'll talk about that next time. But basically, we will stop with this thing, and you can read the books there related to that and kind of look at this. It's kind of an interesting slide, but essentially we're gonna get to ionization energy next time. Any questions? Okay, we're done a little early today. I'm going to stop the share now. Okay, any questions? Okay, very good. So I'll see you all on Wednesday. We're done for today. This is a good place to stop, and we will, based on where I got, I will notify you whether the quiz will be on Wednesday or on Thursday, okay? Any
Dr.
questions?
Douglas.
Here we go. Yes.
Do you have a second to stay after? I had a few questions.
Yeah, I will end this and then we'll go to Zoom again. Any other?
Thank you.
Any other things?
Dr. Douglas,
Yes.
for the quiz, will you give us some time to print out the PDF so we don't have to waste class time to do it?
Well, you could draw on the screen on the PDF if you like, and yes, I will. I'll give you plenty of time to do it, and that's why I'm thinking of having it be Thursday and just have the quiz.
Okay, I don't have the ability to write on the screen, so I would have to print it out. Okay.
Dr. Douglas, and I don't have a printer at my house. So if I need to print it, I need to print it off ahead of time. So I was just wondering how we were going to do that.
Well, can you print? I will email you a link to Nitro PDF Reader, and you can type text on the PDF that way and answer the quiz that way, typing.
Okay. Thank you.
Yeah, and I'll send you the link for that. It's just a download, and you can put your signature on PDFs also and type on the screen. It's very easy to figure out, but we'll work something out, okay?
Okay, that works. Thank you.
Any other questions? Okay, well, we're done the meeting. I will talk to everybody next time.